Hey everyone, most math books when it comes to solving systems of either equations or inequalities would have the learner solve these graphically. That is, using a graph on a Cartesian plane, a coordinate plane like that one, or the one below, or the next one, or the next one. You get the idea. All of them are solved graphically. In this video, I'm going to solve this practice problem with no use of graphs whatsoever. I will be referring to the solution here presented in this textbook, and I'm going to include a link in the video's description box below to this textbook. So I'm going to make use of this a little bit, but I'm going to solve it entirely in a table. Tables are usually disregarded as that's for kids, or tables are slow or not so elegant or clumsy or whatever. Tables are perfectly meaningful and in fact are better solution to this particular problem and many problems than graphs. There are three reasons for this. Try to read this graph. It's really accurately made. If I try to zoom into it, let's see, what are here's the x-axis, this is the horizontal one, of course. It says x on it there. So at 10, do we have, what are the solutions at 10? Is 15 in bounds, or is it out of bounds, or is that on the red line? Is that acceptable, or what's the solution here at 10? Is 15 okay? It's difficult to decide, and even more so, how about 9? At 9, is there a solution there? It looks like it's completely out of bound. In a table, you will see that 9 is permissible and meets all requirements. It's impossible to tell from this whether 9 is even considered okay. So graphs are difficult to read there. Number 2, data is not continuous in this practice problem. Here it's about photographs. Photographs come in whole number multiples. There are 2, 3, 4, 57, whatever. There are no 2.2 photographs or fractional photographs, okay? Just whole number multiples. That means that the data is discrete. It's not continuous, and the graph connected here like this as a line graph is a bad choice, because a line graph means that data is continuous, but it's not. There are no 10.7 photographs here on the x-axis or on the y-axis. It's nonsensical. So what should be done here, instead of a line, there should be small bar graphs here, or bar graph of a small columns. How many photographs are permissible at 1, at 2, at 3, at 4? Lots of little bar graphs, and yes, they kind of form a line, obviously, but they are not. They should not be connected into a continuous line because the data is not continuous. And reason number 3 why I'm solving it in a table is that this graphing stuff may be overcomplicating stuff where there is no need for complication. You need to be able to think for yourself, maybe not outside of the box, but let me give you an example here. So I'm going to solve these 4 questions here. Actually, it says write a system of inequalities. I will solve it without doing any equations or inequalities. Graph the system. I'm not going to graph it. The solution will be clearly laid out in a table. All of the permissible solutions for this photograph situation, and I'm going to solve questions C and D in under 30 seconds without any graph and without any equations or inequalities. So let's read the problem here. Christy sells her photographs at a booth at a street fair. She wants to have at least 25 photos to display, and they are of 2 sizes. It doesn't say so, but it's implied that a small photo, which costs her $4, that's a typo, that should be a dollar symbol there, and large photos cost $10 a piece there. She doesn't want to spend more than $200 on the whole cost of this display. So there are some minimum numbers, 25, maximum numbers, $200, and cost of small photo 4, large photo 10. So how many of small and how many of large can she have? What combinations work? So let's start with this question here. Can she have 15 small and 5 large photos? Let's do something that's requiring, I think, grade 2 level skills. 15 plus 5 is 20, and she needs at least 25, so no is the answer for question C. See, it doesn't need graph, and it doesn't need an overly complicated, elegant solution. You need to be able to think for yourself, kind of outside of the box. Can she have 3 large and 22 small? Okay, let's do the thinking here. 3 plus 22 is 25, so far so good. Now let's do a rough estimate here. 3 large photos cost $10 a piece, that's $30. 22 times 4 is 88. 88 plus 30 is less than 120. So yeah, we are well within budget. Yeah, she can have 3 large and 22 small photos. Done. It can be perfectly well answered without any system, without an equation, without a graph. Done. So for all of the solutions, I'm going to use Excel because the answers can be in a table very easily shown. So here I'm going to start with small and large, and I'm going to use, as the textbook uses, the small is going to be on the x-axis or in the x column, and large photos will be in the y column. And this is just to meet the minimum requirements, that is at least 25 pieces of photos. And over here, maybe in this space, I'm going to calculate the max limits of the system, which is going to be working with the $200 amount. How many photos of small and large can be combined in what combinations closest to $200? Okay, so that's going to be in this space here, and meeting the bare minimum piece count requirement is going to be here as a start. So we can have 0 small photos and 25 large photos, so that adds up to 25. We can have 1 of these and 24 of those, and 2 of these and 23 of those. And now I can just do this with Excel. Here I can just pull it down and extend it. I don't know, maybe that's too many, but whatever. Lots of numbers. It's good. And these can be also continued. Obviously there's no negative photographs, so I'm just going to delete these ones here, like so. Now all of these add up to 25 very easily. So you can have 10 of these and 15 of those, or 16 of these and 9 of those. So all of these look like good combinations because they add up to 25. Now I'm going to put the dollar value of the small ones here and the dollar value of the large ones here, and I'm going to put a formula here. Say this cell needs to be multiplied by 4, and this cell here needs to be multiplied by 10 to calculate its value. So 25 large photos obviously cost $250, and of course the formula can be copied so you can see how it's unfolding. 1 photo is $4, 2 photo is $8. This is the 4 times table here. Let's just run it down. Why not? Now right now we ended up with $332, clearly out of bound, but I'm just playing with numbers here to have enough creative space here. So $250 for the large photos, and we can count all the way down to 0 there. That's fine. So this is the total, this is the cost of the large photos, and very easily I can make a total cost column here as well, and simply add the cost of small ones plus the cost of the large ones there. So $250 for 0 of these and 25 of those. Now a word problem doesn't say that there must be a mix of small and large. It just says minimum 25. So I'm taking 0 small pictures or 0 large pictures, an acceptable solution. So 0 is fine. And what I'm going to do is just copy down this formula. Just why not? So obviously the formula works, and the solutions here can be very easily visualized. I'm going to use some colors. So these are more than $200, all of them. So these combinations here, 8 small and 17 and whatever, 4 and 21 and 2 small ones and 23 large ones, these are not going to work. But these ones do work here. So I'm going to highlight them, or I don't know, put a box around them, such as there, outside borders there. So these are combinations of small and large photos that work. 9 small and 16 large is worth $196. So like I said, it's immediately obvious from the table that yes, at 9, 16 is the answer there. It's clearly there. At 9, it's 16, and at 10, it's 15. It's crystal clear that at 10 the answer is 15 there. Like I said, it doesn't matter how much you try to zoom into this graph, it's not helping enough. No matter how accurately it is drawn up, you can't possibly fathom that at 9 there is a solution point. You can have 16 photographs, 16 large, at 9 small. So this is why I think just tables are useful and shouldn't be dismissed. So this is some solutions that meet the minimum requirement, but I notice here that these zeros can continue down here. You can have 25 small and 0 large, and it's $100. And look, this is also 25 small ones are $104, and that means you have 0 large ones and 0 large ones there. But you know what? It doesn't have to be 0 large. You could put a different number there. I can start tweaking it. How about if we add 1 there and see how this number changes there? It went up to 114. Obviously this works. You can have 1, or you can have maybe 2, or you can have different. Can you have 20? Maybe not 20. That's 20 is just $200 in and of itself. How about, can you have 15? Obviously not. That's too many. Okay, how about 12? Is 12 gonna work? No, that's too many. How about 9? Yeah, 9 works. Look at that. Found another solution with 26 small ones and 9 large ones. That also works. That's well within the specifications here. But so there are other solutions hidden here, but I want to highlight these ones for the moment as is, unchanged, because look at them. If I highlight them like so in a box and get rid of that little line there, you can see that all of these numbers here are less than 200, all of them. There, all of these are fine. I don't know, make them blue, something, I don't know, maybe that blue. They are cool, they are blue. So these numbers all work. Of course, if I copy the formula down one more, you can see that, yeah, that they start going overboard, over 200 here. There, so up to 50 small ones. Obviously 50 small pictures cost exactly $200. With 0 large, this can all be 0 here, and just leave it all zeros here for now. Now, because the problem says that Christy wants at least 25 pictures, so that means that, yeah, she can have 50. 50 is at least 25, but we're hitting a ceiling of cost at $200. So these are all permissible options here for in this boxed cell in column C that are fine. And if you're trying to see any of these on a graph at this scale, you can kind of see that it hits 0 at 50. There's a 0 point there, but again, is 49 acceptable? How about 51? You kind of need a table here to see that, yes, 50, or where is it, sorry, 50 times 4 is 200, so that's the ceiling there. All right, over here on this side, I'm gonna copy some of this stuff here. Let's see if it works out well enough. And I want to lay out data in a different combination. I want to make a combination here. Actually, I'm gonna copy more numbers here. I wanna copy this stuff, but the numbers only. Maybe not 50, maybe just 25 of them, something like that. And see how I can put them in there. Okay, just gonna remove the borders here. There. So in this space here, what I'm trying to do is trying to see how many large photos can you have to maximize this $200 limit. You see that, say, 10 small pictures and 15 large pictures works fantastically well when they meet the minimum requirement, and they are only $190. So you could have one more large picture here, because 10 small and 15 large is fine. But there's another solution, 10 with 16. So I kind of want to lay out here another table that shows this. On the graph, this would be something like 10, oops, what was it? 10 small with 15 large. There, 10 small with 15 large, but 10 small also works with 16 large. Good luck trying to find that 16 again on the graph. Graphs are difficult to read, and you wouldn't know how to make sense of that tiniest little triangle there. 9 works with 16, and it's already $196, and it doesn't really work with 15 pictures or with 16 or whatever, any other combinations. 9 and 16, it's an ordered pair. It's a combination that doesn't have any other options. So 9 and 15 works fine, and 9 and 16 are also permissible. 10 and 15, so 10 small with 15 large and 10 small with 16 large, which is kind of hidden here in this tiniest little corner of the graph. So let's have a look at how this unfolds here. If I want to maximize the number of the $200 amount, let's see how many I can have starting, I don't know, somewhere there. There's a reason why. You'll see, if I copy down this formula there, and not formula, oops, not there, okay, then this formula also further down. Yeah, so far so good. So it's just mirroring the numbers from the 4 times table for the cost of the small pictures. So can we have 20 pictures here? No, that's over the limit. So maybe 19 pictures there, 19 pictures, so that's not exceeding. So this is about maximum limits. That's not exceeding that. So 25 is too much. Can we have 19? Yeah, can we have 20? Yeah, 20 works there. 20, so that's well within the $200, and 19 works there. How about 19 there? That still works, and it's pretty close to $200. How about 19 there is the largest number? No, that's too many. 18 there, yeah, okay, 18 works. How about 18 there? That also works, and there's $4 left, but just gonna leave it there. Will 18 work there? Yeah, 18 works there fantastically well. How about there? 18, no, that's too many, that's $204. So let's drop it down to 17. So you can have a maximum of 17 photos here. And let's look at the pattern here. 19, 19, 18, 18, 18, 17, 17. If I try to enter 17 again, it's too many. I'm gonna have to switch to 16. So 19, 19 twice, 18 3 times, 17 twice, 16 gonna be 3 times. So I'm just gonna fill it in like so. 15, 15, 15, 15. Next number is 14, 14, 14. Next one is 13 and 13 twice. Nothing is more than $200. Next is 12 and 12. And one more 12. Yeah. 11 and 11. And then 10 and 10. And one more 10. That's all fine. That's well within 200. Let's extend all of these formulas further down and see what else we find. There could be good solutions there. Okay, it doesn't help because it just copies everything. So just copy the formula independently. These need to be going up like that. And this formula just like so, and that one just like so. Okay, let's see. What if I put 10 here? Yeah, 10 works. $200. Next one, 9 and 9. 9, 13. No, that's too many. Then 8, 8 and 8. 7 and 7. 6, 6 and 6. But it's too many. 5 and 5. 4, 4 and 4. Oops, I skipped one line. Just extend the table further down. Let's see. I guess it gets to be extended all the way to 50. None. Let's copy the formula. Yeah, $200 there. Let's copy these ones there and those ones there. Okay, just quickly finishing it. So 3 and 3, 2, 2 and 2, 1 and 1. Oops, 1 and 1, and that's gonna be here 0 and 0 and 0. So that's how the table looks like completed, and all of these look like good numbers, none of them exceeding $200. So it looks like all of these are okay except one thing. Some of them are less than 25, because 0 plus 20, because this is about maximizing the possible cost of this. So 0 plus 20 is less than 20. And let's see, yeah, the first one starts 8 plus 16. That looks like 24. So all of these look like good combinations here that work. There, we put a box around them like so. There. So how do these two tables work with the range of permissible numbers shown like this? Okay, so at 9 you can have either 9 small pictures, you can have 16 large pictures, or 16 large pictures. At 10 you can have, this is the minimum side here on the left, and 10 you can have a minimum 10 large pictures or a maximum of 16 pictures. Back to the graph. At 10 it's either 15 or 16 there on the y-axis. At 11 you can have either 14 large pictures or you can go up to 15 large pictures. So at 11, good luck with that, you have 14 and 15 as permissible numbers there. At 12 small pictures you can have at least 13, or you can go up to all the way to 15 for with large pictures, and that's well within $200. So it reads horizontally like so in rows. If you want 17 small pictures, you can have a minimum of 8 large pictures or a maximum of 13 large pictures, and anything in between, because then you hit the ceiling there. So at 17, okay, something that's easier to read on the graph is at 20 there should be 5 large pictures at the minimum and 12 at a maximum. So let's see how this looks like at 20 here. There is the 5 and there is the, yeah, good luck with that number there. 5, and what was that number? Yeah, you're gonna have to go back to the table. Oh yeah, 12. So at 20 we have 5 and 12, and again, good luck trying to get 12 out of the table at this scale or at this detail. So that's why a table with the numbers laid out like so, and using it sensibly, that these are the minimum solutions here on the left side, and these are the maximum solutions that go with the whatever value on the x-axis here. These are the minimum numbers on the y-axis that go with it, and these are the maximum numbers on the same x numbers on the x-axis that work with the y-axis. Okay, so that's how the solutions look like in a table, and everything else is that's out of bounds. So numbers continue, but solutions don't. So I'm just gonna get rid of all this there. Well, it's just 3 numbers there. Okay, there. So now it's neat. So these are the solutions to Christie's problem, and to determine how many of these and how many of those she wants to have, I'd say she needs to consult the tables. Thank you very much for watching. It's been a long video. I'm hoping to put more sense into a complicated math, and I hope this video helps you a bit. Using tables and making sense of tables that are usually ignored or disregarded and considered less elegant. So there, tables are perfectly fine, especially when data is discrete.